Hi there.
Hey, can you hear me now?
Yeah, I can hear you. Did you see you obviously clicked the link then?
Yep. So I got in, so I think it's just waiting for other people. You let everybody know. So everybody's been coming up with good questions.
I had a bit of issues, as you probably saw on Facebook, installing it. But I've got they've got this a CDF forum, CDF open forum.
Right.
So they've got build questions and
right.
questions. And they answered it within about half a day. I put up a question.
Yeah. So I'm still of the opinion it's the best first step.
Yeah, I mean we have to try something. You have to try something out to see what's happening.
Right. Okay. So I was just saying that based upon even all the objections that people brought up, and based from what I've seen of OpenFOAM, I haven't gone to any depth. But everything that I've seen of it, I see all those objections being addressable one way or another. I'm just saying that all the objections you brought up, good objections, good questions, because guess what? Those questions are talked about in the forums that I've seen, and from what I've looked around.
I'll just email Paul Avillette in case he hasn't looked at Facebook.
It took me a moment to get all that going, and I saw you, Dave. You're on the old meeting link.
What? Can you hear me?
Yeah, I saw you after the meeting had been stopped. I used the old link, and I saw you on there. So okay, I think that you can actually restart the meeting.
We can just restart the old meeting. Yeah, maybe.
Maybe.
Right. So based on what I've seen, my opinion, and everybody's got their own opinion, is that I think OpenFOAM is still the best thing to try first. To see if it can answer all the questions. From what I've seen, they've at least discussed it in everything that I've seen. So I think it's a good place to start and make a go at it. And I also think that AWS having a common build that's easy to share is the way to go also. So that's why I put that in the plan. And I hear all the objections, and I still think that's the best plan. What are your guys' opinions?
Yeah, it's just a matter if we can get it started. It's when it's running, I can make an evaluation, not before.
Yeah, sure. There you go. Well, we'll wait and see. I think everybody's of the same opinion there. So you got to make steps and then adapt.
Right. It's just too early to get married to one system before
No, you'll never be where you shouldn't be.
Then you'll get a better idea of what needs to be done. If it doesn't work, then you'll get a broader idea of what's going on. Right. It might work to a certain extent, but you get more knowledge on what's actually happening.
Right. So the first thing we know is we don't have motion, and we want motion. And we know that fluid dynamic systems have motion. So
we do have motion. But it's constant linear velocity. That's what.
Well, we can't see it. When we run those equations, Paul's equations, we're not seeing motion as one of the outputs to view. What we're seeing is quantification within specific points of space.
There's motion initially, and then it stabilizes after a certain point. But I'm a little bit fuzzy because it's been a while. But as I was going through my emails, I mean, there was linear velocity was seen, and that was actually a concern because you would expect if you have gravitational acceleration to see acceleration, not a constant linear velocity. And so there was motion, but there was no. Well,
motion was.
So we're simplifying. It's just we're just doing a simplified model. You can't include everything in the model. You just include things you want to investigate.
So the motion that we were working with, my understanding that the motion was an input, that it was this motion field that was being used as an input to seed the creation. But the outputs, all we're seeing in the outputs is a quantification of how much geons, exons, yons are in any specific location. We're not seeing this group of exons move from here to there. So that's the motion we're not seeing.
If I remember correctly, there was. And I have emails that to that effect.
If you've got that, if you can see motion out of those equations of, okay, we've got these exons, okay, so we've got it, because it was like how many exons and yons are in this space. It was not how many exons in this part of the space move from here to another location.
It reminds me.
It was transient, but I guess to answer that real quickly is it was seeded with like a Turing waveform, which was composed of exponentials, and then it went away. So it's just sort of like throwing a rock in the pond, essentially. But then afterwards there was motion that was generated and continued on from there, and but there was no. And furthermore, going through my emails, Matt had done some more work with Paul, and they said that they had actually created what's called, and I wish Paul was still here because I was going to ask him about that, was they had seen.
But I'm not sure if I sent him an email, so I'm not with the link.
Yeah, well, maybe if it comes back a little later, but they had actually created a Tori waveform. But it wasn't a vortex.
It reminds me a bit about in physics, like degree level physics or A level or high school or whatever, when you're looking at Maxwell-Boltzmann statistics, the behavior of gases, and you input the average velocity. So you're looking when you're inputting the average velocity, all the other particles are distributed with a certain amount of velocity. So Maxwell-Boltzmann statistics, when he's analyzing the motion of particles in a gas. Do you recall that?
No. Okay. So I don't know if I've ever.
It's just Maxwell-Boltzmann statistics is looking at the behavior of gas particles in a gas.
How can you say
how they interact?
Coarse approximation.
Okay, so that's a motion. That's something that would be motion. Okay, the other one where they were seeing that toroidal, what you call motion, what was measured was the quantity in a point of space. So you had these many exons and yons. You ran the equations, and then later on in another point of space, you saw a large, in this point of space, in point one in space, you saw, okay, we got a whole bunch of exons. And then a couple seconds later, you see, oh, we got a whole bunch of exons here. You don't know if that's because the exons were moving. You don't know, dissipating, reaction, diffusing. You don't know if that's through diffusion, or it's because of reaction, or a combination of the two. Okay, so you don't know if these exons moved over here, or new exons were created in this space.
Justin, you said that the open foam incorporated a reaction diffusion.
There was an add-on. Some of the links that I was showing you had reaction, some of them had diffusion in them, so it looks like they were doing some reactions and they were doing some diffusion too, and I think some cases they're doing both together. Are
the particles in SQK, the model G, are they a bit like the brusellator? Are they behaving like the brusellator?
My impression was that it was an example of the brusellator or a variation of
the brusellator. Yeah.
That the brusellator was slightly simpler equations. It didn't have as many pieces because I think you had to have the 3 or 4. You had to have the 3 axons. You have to 3 of them. And I think like brusellator only had 2.
Because at the moment, Paul's using concentration of X, Y, and Z.
That's the output. That's what's being represented in the output. Okay, in this point in space, how many exons, how many yons, how many geons? At this point in space, and this point in time, how many exons, yons, and geons? It's not saying, okay, we had all of these exons and they moved. So it's difficult to get, without that type of output, without that type of view, it's very difficult to get the vortical motion. It's difficult to see it. We're only seeing one slight feature of the motion. Okay, whereas with a fluid dynamic system, you're seeing, okay, we got all of this and it's moving all over here. You're seeing more of what's happening from a motion perspective, that this group of exons and yons is moving here. It's not just, okay, the quantity's high here. It's all of these guys moved here. And if you see these guys moved here while these guys moved here, then you've got, if you got these guys moved over here and then these guys moved over there, then you've got this vortice that's forming. Okay, we can't see that with the type of information that's coming out of those equations. It may be possible that we can pull that type of information out of those equations, but I don't see that those equations were built for pulling that type of information.
The Model G equations, differential equations.
The type of system that's built for pulling that type of information out is a computational fluid dynamic system. People want to pull that information out, so they created computational systems to pull that information out, and that's what a CFD system is. People want to pull specific information out, so they build a specific computational tool to pull that information out. So that's why I say go to a CFD system, because I'm looking at these other systems and says, well, where's, X, Y, and Z? Well, they're not there. Then what type of system has it? Oh, CFD does that. That's a standard thing. It's used all over the place by specialists for that specific task. So you go where the tools are. And so you naturally say, hey, we want to see how things are flowing, fluid dynamics. Okay? That's what we're trying to look at, fluid dynamics.
A lot of times those systems are designed around well-known phenomena, and so it's not, we don't have to prove first that it's going to work for a very unique system such as this.
Okay, so fluid.
We're just treating. Say the ether is a bit like the weather system on Earth. We're just taking a model of the weather system on Earth, and then shrinking it down to the microscopic level.
We're adding reaction.
We're just treating it. We're just trying to model. Take a macro system like a fluid or the weather, and assume and pretending that that's the ether on a microscopic level.
Right. So, and Brendan mentioned this earlier to your point, Michael. He said this is just the standard computational tool. It's not this physical system, that physical system. People use this computational tool for all sorts of different things. It's just the general problem. And in some cases, they talk about inertia, and sometimes they talk about density, and sometimes they talk about this or that, because for each one of the different fluid dynamics problems, sometimes they're looking at these other features, and people have added it here or added it there. So it's very much that's what this type of community does.
It reminds me of
not all doing the same physical problem. It's an open source community, and everybody's doing very different things. And so they add this feature and that feature when they need this feature, that feature. And from what we saw, there were a lot of different people who needed reaction, a lot of different people who need diffusion. Those are the two big things. But, I believe that the gravity, the inertia, all of these types of things have been talked about too. Besides, so within our system, what's gravity? Gravity is the dissipation, of geons, where the geons, having dearth, so the whole bunch of geons want to flow in that direction. That's how you get gravity.
And it could also be all the concentrations of all the particles moving, but through, what appears to be gravity. And Matt had actually done that in 1D, but he did not do that in 3D.
Could you clarify a little bit on what you're saying? That because the flows that we have are not so much the geons and exons, it's the underlying, I think it was alpha and beta or what have you, that are used to create the exons, yons, and geons. And that those are ether flows, and that those are what's generating, that's the sort of like the source priming thing, because that's the underlying ether flow.
It reminds
me the concentration of exons, yons, and geons.
Can you ping Paul again?
Email him, you mean?
Yeah, ping him, yeah.
I've emailed him. Okay, I'll just do it to Paul then. Let's just try that. Paul. Paul, I'll just put Paul.
So there's one other thing that I wanted to bring up. while you're doing that, Brendan. It's sort of like an off topic. So there have been experiments like Koryov, one of these, and I brought this up to Paul. There's one of he's an astronomer, and he was a Russian astronomer from the 50s, and he had bacteria as his measuring tool. And the bacteria grew much faster when he pointed his telescope, which was completely blacked out, in the direction of the sun, and also a couple of different variations. And when we say the direction of the sun, not 8 minutes later, when the light would reach, he was getting a response by the bacteria almost instantaneously, like 1 billion times faster than the speed of light.
Yeah.
Justin, it reminds me of gas laws. You know, when you've got the kinetic, you treat the kinetic energy of one particle, then you've got pressure, volume, temperature, and mass. And you're looking at the kinetic property of like one particle, and then you're putting it into a bigger system where you've got pressure, volume, mass, and temperature. So you take it, and then you're kind of getting the average velocity. What's the average velocity? That's like the temperature. The velocity of the particles are the temperature.
Right. That's exactly what temperature is. So and that's the thing about the subquantum kinetics and Model G, is that everything is that type of behavior.
You've got sort of like you've got one little particle which has got a mass, which has got kinetic energy, mass, and velocity, and then you're inputting that into your kind of like you've got those little, so you've got it traveling randomly in a box, in a kind of hypothetical box. And then you're kind of like, from that you get then you're going into then you're inputting that equation into a bigger, more general system of volume, pressure, and temperature and mass.
Right. So you get that at the macro micro level, but you also see the same behavior at the cosmological level.
So you can tell.
But then with the subquantum kinetics, use that same type of behavior, and you describe everything at the particle and subparticle level. So when you get a vortice, that's the reactions of all of these subparticles interacting. Okay, so that's the motion of it. It's you've got all these subparticles that are reacting, and creating a vortice and all of their behaviors are described by the same type of subparticle kinetics reactions. Okay, and that behavior tells you what's happening at the particle level, okay, and the nuclear level. So no longer do you have to worry about, this particle is moving from this level to another level, and it's just energy states around an atom. No, it's no longer that. It's this moved up here, so all that motion of all those subparticles interacting gets transferred into motion instead of at the subparticles reacting level, but as at the atom, the full atom motion. So you're getting a transfer. So it's always the subparticles and how they're reacting at a interaction perspective. Just like in a heat type experiment where you get the macro level description of all those subparticles interacting and their motions. You're getting that motion being transferred into the motion of the full particle. So that's now the heat of all the particles moving. Okay, so you're getting all this motion that's happening at the within the atom. You're getting all that reaction in the atom to that interaction at the atomic level where all the atoms are moving around. Okay, so that that is what we would consider heat. So you're getting a direct transformation of motion at the subparticle level being transferred into motion as the atoms are moving back and forth. So it's the same level of description. It's the same type of description. All heat and temperature becomes this motion of particles. Okay, it's no longer, hey, we're talking about levels or states of energy around an atom. That's no longer part of it. because that state is motion at the subparticle level. Okay, motion of particles at the subparticle level.
Speaking of motion, that reference I alluded to earlier, that was in that paper for Model G. I posted a link to it, and that was actually a motion of a soliton and a G-on gradient, so a gravity gradient, and they saw some initial acceleration, and then it tapered off to a constant velocity, and I think that was one of the reasons for the purpose for this extra modeling here is that, well, okay, that's not reality, that's not what's really going on. So
could you share that again? I kind of missed what you were talking about there.
Okay,
go over it because it went a little fast.
Yeah, if you look at the paper and on page 19, you can see a graph.
Share it again.
Yeah, I'll link to it in the chat. You can see a graph, and it shows, it was modeled in 1D, and it shows the particle velocity versus time. And I think within about, I don't know if those are seconds, I have to verify, but very quickly it tapers off to a constant velocity, which you wouldn't expect. So in reality, so that was one of the reasons for, they'll say, well, maybe there should be some vortices going on here or something like that. And but he never was able to simulate that in 3D. And so it's possible that some information was getting lost, or the initial conditions weren't satisfactory. So it's like, well, what are we trying to model here? And I think that's a fundamental question I'm driving at is what is the experiment, the mathematical experiment that we're.
Okay, so you're measuring particle velocity.
It's a bit like if you think of like a when you're measuring gravity. Say you've got a pendulum, and you're measuring gravity from the swinging of the pendulum. You've got the length of the string, you've got the mass of the bob, and you've got its period. So physics is a bit like that. You're kind of like you're zooming in to look at one aspect, to draw out one dimension of information out of a model. So you can't model on a pendulum when you've got a pendulum with a mass on the end. You're trying to measure gravity. You can't model every single particle in the string in the ball. Right. You just make a what do you call it? Approximation. You make an abstraction. You abstract it.
Yeah, if you could get to 2 dimensions, you could with some type of measure of velocity. Now, it's the velocity of all of the particles, yes. Or is it?
They're referred to as a soliton, or all the.
Is it velocity of the soliton, or is it velocity of all the subparticles that are making up the soliton?
Yes and yes, all of the above.
So they're all moving at the same speed.
Well, initially, yeah. Well.
So what we're trying to see is, and you may not be able to see this in a one-dimensional model, is we're trying to see what's the motion of the subparticles relative to each other. Even if they might all be moving together, we want to see the motion relative to each other.
I wouldn't agree with that completely. In that, essentially, you just want to see if the system provides some results that would be reflected in reality. And the more detailed, the more granular,
okay, so we're
trying to computationally intensive it gets and complicated it gets.
We're trying to flesh out vortical motion.
Yeah, what I was thinking.
There's no such thing as a real one-dimensional. Well, okay, the pendulum might be a one-dimensional type reality thing, but the types of phenomena we're trying to flesh out, we're trying to pull out is so.
Well, it's a premise that there could be vortical motion, which is not showing up in the model, and then that's why we're not getting an acceleration in a gravity field. Okay. Instead, we're getting a constant velocity.
So my point is that we're not using a computational system that is regularly used to represent motion between element components. That would be a fluid dynamic system.
Can you see the screen,
such a
Justin?
computational system.
Justin, can you see the screen? This is Spin in Physics, Wikipedia. Can you see down here? They're defining spin as this kind of term here.
Yeah, it's a quantum. It's, you know, it has nothing to do
so
with,
it's defining it by magnetism.
it's a defined thing. It's not a gradation.
You know, so you're in a sense you're homing in on one little part. You know, you're homing in on one aspect of the physical model you want to look at.
Right. So you need to have a computational system that you can get the information.
Yeah, that's right. Because from my understanding, from my memory of doing quantum mechanics at BSc level, is that they were saying, oh, spin. They were talking about spin as being angular momentum of the particle.
We're talking at a level below.
Yeah,
they're looking at the particle level. We're looking at the subparticle level. Okay, so we're defining the spin as the reaction of all and the motion of all the exons, yons, and geons within a space.
I seem to remember when I did it, they were saying, "Oh, spin, you can't visualize it on their level." I'm not saying that that's true.
Using the models, okay. So this is the
they
problem.
said that you couldn't visualize it. It was some abstract. It was some quantum abstract thing that.
That's the problem with their model. Their physical model lacks the ability to visualize that. Okay, they came up with just a general mathematical abstraction. They're not doing things at. Okay, that's the severe flaw at the quantum mechanics level. Okay, if you're a computational scientist, say you need a computational model that can do X, Y, and Z. It's not only their computational model doesn't, their physical model doesn't have that. Okay, so you got to sort of say we can use some of their equations at a gross level, but at the sub level we got to go to a CFD system with the addition of reaction diffusion. CFDs are more complex. When these physicists came up with this stuff, they didn't have CFD around. They came up well before we had computers that could run CFD systems. Okay, this was well beyond any fantasy they might have had.
It's also subquantum kinetics, from what I understand, can predict a fair bit, can make a number of predictions and experiments that can be shown to prove a number of different physical aspects that.
Right. So that a lot of that is at the astronomical level.
Yeah.
But some of it's at the subatomic level also.
Well, the soliton, it's got a distribution that's pretty approximately similar to what they measured on what was that, atomic force microscope. So, and that's in the book. And so those are the things that they're like, okay, great, you know, that was published. This is the model represented this accurately, so that's a good thing. But then, then why don't just go with the model as it is? Well, when you try to actually test it out in a gravity field, it doesn't continuously accelerate. And
so you're saying let's use the equations as they are. The equations, it's a mathematical system with limitations. Okay?
I'm not saying that actually. Okay. I'm saying that based on their simulations, that they didn't get that result, but they only did it in one dimension, and I mean it could be the
and they can't explain new energy systems and anti-gravity in conventional physics. So there's a whole load of different types of new energy systems that are very
there's a lot of behaviors that can't be easily explained by
electrogravitics is completely impossible.
It's just one, but even at the biological level, there's a slew of different things that can't be explained by the conventional model.
Well, I was referring to
experiment after experiment after experiment.
The results of Matt Pulver and Dr. LaViolette, that they got the soliton, and the soliton was a good representation of what's been measured in the lab. But then when they took it to the next test and put it in a gravity field, that's when it failed.
Okay, they don't even have they didn't even use the computational system that you need in order to get that information out. You have to pull information out. You have to have a computational system that has reaction, diffusion, and fluid motion. You want to see the vortical motion, you got to have some type of fluid representation. I've said this like 10 times here. It's like, and before, it's like, you can't use the equations Pulver was using to pull that information out. People don't use those equations to pull fluid motion out. Use a fluid dynamic system to pull fluid motion out. Can you use other mathematical systems to it? Yes. But what's the most common system that's used? A fluid dynamic system. There's a whole field around it.
Says we've got 10 minutes left for the 40-minute time limit.
So it's like,
anyway, well, I think, Justin, it's just a question of trying it out and seeing how far.
It's a question of trying it out, but it's like, I expect to get this out of it. It failed because, it doesn't have the things in it to begin with that you need. It doesn't have the basics.
Well, it did well enough to be able to simulate the soliton. It did a pretty good job of it in that respect. And that's why
you're trying to look at vortical motion. You want to get vortical, you want to get any motion inside of the thing, you got to do fluid dynamics. Okay, if you're just looking quantities, okay, you can see something there. But if you want vortical stuff, right?
Well, that's,
we don't see vortical stuff there. Yeah, duh, because it doesn't have anything. You're not going to see any motion at that level, except at a gross level.
Well, you may have vortical motion, but based on my conversations with Matt and Dr. LaViolette, it's a postulate. But Matt wasn't even necessarily leaning in that direction, and Dr. LaViolette, he's open to any possibility. So I mean, it's just one line avenue of investigation, and the models was so far worked so well that it was published in a paper, and it was published in the book. So I mean, maybe the ETD stepper could be okay. I mean,
it's great stuff. I mean, they did great stuff, but this whole group is focused on vortical stuff, and basic thing is so like a month ago, 2-3 months ago, people were saying, well, what do we do? What do we do? What do we do? Well, you want motion, you use a system that can get motion out. If you want to do vortical, you use a system that will have it. That's how you solve the problem. You got a very specific problem, you use the standard tools to solve the problem. And you're saying, well, let's use all this stuff. Well, that didn't solve the problem, and it's not going to solve the problem. It's like I want a wrench that will, turn my pipe. I'm not going to take a standard hex wrench and use it on the pipe, that's of a different shape and form. You use something that fits. It's real simple, Michael. Just use something that fits. It's not that they did anything wrong, or they were doing the first initial experiments, and they're great experiments, and they were able to see formation. And that's what they did.
Improvement in those experiments also. I mean, even with that method that they're using, I mean, obviously you're going to lose information in a 1D simulation versus a 3D, and so I mean, I see there's room for improvement even just in that realm. But if this is what it's all about, it's just about getting vortical motion, well then I guess I couldn't disagree that CFD would be helpful, but then I wonder about the mass issue. It's just but I haven't looked into
we don't know the mass. We don't know the mass. So we just have to put any old mass in. We don't have to try put a certain dimensionless mass in or something like that. And then see how that works, then adjust it. I think it's trial and error.
As Dr.
Then you look at then you've got a measurement on a macro scale, and you adjust the model so that it fits the measurement on a macro scale, and then you can. I mean, that's a very simplified way of explaining it. But
right, okay, so remember mass from the
equation. If the equation predicts something, or that you can measure on a macro scale, then you know that value anyway. So then you put that you put that, you then adjust your model, and so it's the same as the the real world measurement, and you can adjust, and you can find out. I mean, that's a very, very simplified way of saying it, which is something which is probably much more complicated, or to take many steps to get to. But so you have a bit like reverse engineering. You have a system where you're making a measurement, and you're getting a certain result. So therefore, if you know the macro scale measurement value, you can then adjust the model until it fits that real world result.
Right. So you can add mass in, you can add inertial motion in, you can add all of these things
I mean,
in.
we're at the very basic stage. We're at the very basic level.
And the very basic stage is we need to get some type of measurement of motion, and we need some system that will measure motion.
Well, we did have a system that measured motion.
Okay, you're talking motion at a very gross level. We need something that's looking at motion at a finer level.
Well,
and so that system didn't have it. Those systems are not used for that, for looking at fluid motions. You want to see fluid motion, you want to see three-dimensional fluid motion, you use a system that does that, and that's CFD.
Well, you got to be able to match it up to physical reality at some point, and that's the motion that we can observe. And that's the motion that's probably going to be able to be most useful for back engineering it and getting the values that we need. So if you're going to back engineer it, you can say, well, what kind of spin do I need in a gravitational field to get an acceleration of the soliton?
Yeah, I mean, we don't know that yet. We're just setting up the model.
Right. So moving back to
that bit by bit. I mean, sometimes people can spend. I was told by my supervisor once, people can spend their whole lives just on one problem, just trying to solve one problem.
Right. So stepping back to the outline I had.
When I was doing something on my PhD that I couldn't get it working or something. He said, some scientists spend their whole lives just trying to solve one problem that they confronted with.
Did you finish your PhD?
Sorry?
Did you finish?
Yeah, I completed it.
Congratulations. When did you do that? A long time ago?
January 2017.
Oh, real recent. Congratulations.
Yeah. Thanks.
That's good. What was it in?
It was in magnetic induction tomography physics. So it's basically, I was using magnetic fields to image inside metal enclosures for which had applications in airport scanning and security. Cool.
But it does have a lot of application from a subquantum kinetics perspective, I believe.
Well, I did. It was mainly electromagnetism and tomography. But when I did BSc and MSc, I did my MSc in particle physics, and my BSc I did in physics straight, and that involved quantum mechanics and.
But magnetic flow is really flow of exons and yons, okay? Because electromagnetic theory is one combined thing. So I think those flows that you're talking about is something that can be is represent, because we were talking about what's the motion of exons, yons. Well, you've got within particles, but you can also have outside of particles, and so that's what the magnetic field would be. You've got the exons and yons that are creating a flow, and so you're getting these flows of exons and yons. And that's how do those flows go through that metallic wall? So I think this is very pertinent to it's not the vortical motion per se, but it is motion of exons and yons. So it's very applicable, I think, in this space.
Would it be helpful to actually just create a mathematical model of something that is already spinning, and then put it to a test, such as in the gravity field, and just to see if that the spinning has any effect at all, and providing the results that was desired, which is some.
What they do in particle physics, when they've got an equation of that describes a particle.
So that's the problem when you're talking about a simple equation that talks about spin.
I mean, we're
You've got a single equation that represents it. And so you have this motion, it's a single equation. You can't break it into pieces. In order to break into pieces, that's what CFD does. That's what FEA does. Okay, you break the motion of some large object into an equation for the entire object, and the different points in that large object is a simple equation. Okay, that's all you could do back in the 30s, 40s, 1800s. They could use equations. In today's computational world, we can do the computation where you have, okay, this subcomponent of that larger spinning object, we're going to measure what's happening there. We're going to measure what's happening at every single subgrouping within that computational space. That's what.
And there may be an experiment we can do on it. There may be an experiment, not that necessarily we can do, but someone else could do, which